Hi everyone. Today we are presenting our project on Twitter sentiment analysis, and this is our team. This goal of the project is to analyze tweets and classify those as positive or the negative using the machine learning techniques. And we used a large Twitter data set for the followed steps like data processing, modeling, and evaluation to build an effective sentiment predictive system. And next, please. The dataset we used is called a Sentiment 140, which contains around 1.6 million tweets collected from Twitter. Each tweet is labeled with the sentiment, either positive or the negative. For this project, we only focused on two columns, the sentiment label and the tweet text, since these are the most relevant for the sentiment analysis. Next, please. In the data cleaning step, we first converted the statement label from 0 and 4 into the similar binary format for the zeros and ones. Then we removed any missing or empty tweets as they don't provide useful information. We also removed duplicate records to avoid basic into the data. Finally, we kept the text in its raw format without applying processing so that different methods can be tested later. And the next, please. Um, since the original dataset is very long, we created a small and balanced dataset with 15,000 tweets, evenly splitted between the positives and the negatives. We also performed some basic analysis and observed that most tweets are relatedly short, which is typical for the social media data. And overall, after cleaning and preparing the data, it is now ready to use for the building, machine learning, and the deep learning models. Thank you. Next.
So in the pre-processing stage, next page, please. We design pre-processing pipeline to examine how different level of test cleaning affect model performance. We start with pipeline A, which is basic cleaning. It includes converting text to lowercase and removing URL, mention, and punctuation. This serves as our baseline. Then pipeline B adds store words removal. This step remove common words like the and is, so the model can focus on more meaningful tense. Pipeline C further applies stemming, which reduce words to their root form, such as converting running to run. Pipeline D use lemmatization instead of stemming. It converts words into their basic dictionary forms, which help preserve more thematic meaning. The key idea here is that we keep the model the same and only change the pre-processing pipeline. This allows us to clearly compare how different pre-processing strategies impact model performance. Next page.
Next page, please. After building these four pre-processing pipelines, the next step was to convert the text into numerical feature matrices, which are required for machine learning models. I use two vectorization methods across all pipelines. The first is count vectorizer, which counts word frequencies and serves as a baseline. The second is TF-IDF, which downweights common words and gives more importance to words that help distinguish documents. This is useful for Twitter data, where word usage varies a lot. Instead of selecting one setup directly, I built an experiment grid with 14 configurations. These vary by n-gram range and feature size, producing 56 feature matrices in total. After comparing the results, I selected three configurations for each pipeline: TF-IDF with unigrams, TF-IDF with bigrams, and convectorizer with unigrams, all with 5,000 features. This results in 12 core matrices which are used in the modeling stage. One finding on next page, please. One finding from this step is that pipeline A has lower sparsity than the other pipeline. Pipeline C and D have almost identical sparsity. This suggests that stop word removal is the main factor affecting feature structure, while stemming and lemmatization have little impact. All matrices were then prepared for model training, which leads to the next section. Next page.
Next page, please. In this part, I use the logistic regression as a baseline model to evaluate different pipelines and the feature engineering method. Specifically, I test the 4 processing pipelines and 3 feature engineering methods. In total, this result in 12 different combinations. Next page, please. Here are all the results of the model. We evaluated the model using accuracy, precision, recall, and F1 score to select the best combination. And we can find the accuracy ranges from 0.749 to 0.776, showing stable performance across different combinations. So the best result was achieved by pipeline A with TF-IDF unigram with the accuracy of around 0.776. This shows that the unigram feature performed better in this task. Next page, please.
All right. So in this part, we focus on advanced modeling for sentimental classification using the same dataset split and feature the inputs as early stages. We test for 2 stronger classifier, linear SVM and SCD SVM, to examine whether they could be improved for predict performance. To keep the comparison fair, the all models were evaluated under the same condition using standard classification metrics, including accuracy, precision, recall, and F1 score. And this slide is talking about the 2 comparison advanced model under pipeline A using 3 features configuration across all the settings. SGD's SVM achieved higher F1 scores than linear SVM, indicating stronger and more consistent performance among the feature types. A TF-IDF diagram produced the best result overview, suggesting that richer text representation helped improve sentimental classification. This finding shows that the chip's model performance depended not only on the algorithm itself, but also on feature representation.
And so for the project, we learned a few key things. First, data quality really matters. Cleaning the data set made a big difference for our results. Also, interestingly, simple pre-processing actually worked very well. So the plan A, which is just basic cleaning, performed as well as more complex methods. So more complicated works doesn't always mean better. We also saw that the TF-IDF features work better than the basic count features, and the stop word removal had more impact than stemming. For future work, we can try deep learning modules like BERT, improve preprocessing, and use a larger dataset to get better performance. Next slide, please. So to warm up, we successfully built a full sentiment analysis pipeline. We start with the raw Twitter dataset. We clean it and turn it into a structured dataset for modeling. Then we tested different pre-processing and feature engineering methods. Our results show that the performance is quite stable across different setups, and the best result came from the TF-IDF with a simple preprocessing. Our final module achieved around 0.776 accuracy, which is a solid result. Overall, this project shows that the simple and well-designed approach can still work very effectively for real-world settlement analysis test. Next slide, please. This is the reference page for our works. Next slide, please. And thank you for listening to our presentation.